guys will notice that this is one of your homework problems, right? There's one little typo in the actual homework problem, so this isn't entirely like your homework problem. I forgot to ask you about the process at 263 for your homework. But here's the way this is going to work. You always have, for the delta H's, that H of T2, well, we already wrote that up here. H of T2 is H of T1 plus integral of C sub P dt. And if you remember from the last exam and from the review session that we did for the last exam, when you put this all together and you take H of the products minus H of the reactants, delta H is delta H of the products minus H of the reactants. And you plug in this whole expression for H of products and H of reactants. So it'd be H of T2 of the products minus H of T2 of the reactants to get delta H of the reaction. What this all ends up coming to is that delta H of T2 is equal to delta H of T1 plus delta C sub P plus the integral of delta C sub P dt. Right? You guys remember that? Mm-hmm. But in the case that CP's are constant with temperature, then this can come out of the integral and you don't have to get it. And that's why you get the delta C sub P. So you have delta C sub P dt. For this guy, your delta C sub P is 39.7 minus 75.3.
37.4, negative 37.4. Oh.
What was it? Who's this guy? 40 minus 75, whatever this is. So you plug that guy in for delta C sub P.
37.9.
37.9.
36.
Oh, no. You put 39.7.
Oh, it's supposed to be 37.9. I'm dyslexic. So here's your delta C sub P, right? So you just plug that term in here and integrate dt, and that's just dt, or T final minus T initial. And so you get this expression that delta H of T2 is equal to delta H of T1, which we said was negative 6.03. Well, I said that it's a little, yeah, it's fusion. So we're going from liquid to solid. So we know that heat is being released. It's kind of a trick. You have to look at the problem and really ask yourself, what's happening here. So the delta H of fusion is 6.03 kilojoules per mole. But what that means is that when water goes into the solid state from the liquid state, it's releasing that heat. So you actually put a negative sign on that 6.03 kilojoules per mole, right? So you get 6.03 kilojoules per mole, and plus whatever that is. What's 40 minus? That's like 35, about 35.
That's like 37.4.
What's that?
Negative 37.4.
It's negative 37.4.
Yeah.
Times T final minus T initial, right? And you grab that equation. And so those are your delta H's. Your delta S, when you plug this guy in, the same exact way that we did this one, you're going to get that delta S of temperature 2 is equal to delta S of T1 plus delta C sub P, the integral of, if C sub P is constant, it comes out, so it goes delta C sub P times the integral of 1 over T dt, right? Because we said that the change in S goes as C sub P over T dt from initial to final conditions. So C sub P comes out of the integral, you get that term delta C sub P, integral of 1 over T dt, and all of that ends up equaling delta S of T1 plus delta C sub P times the natural log of T final over T initial. And so now you have terms. I want to get through this so we get to the next problem, so I'm not going to actually plug in the numbers. But now you have terms for delta H of T2 and delta S of T2, right? And you know what T2 is, so all you're left to do is plug in the appropriate del C sub P's and natural logs of T finals over T initials, solve for delta H, solve for delta S, plug them into this expression, multiplying by the appropriate temperature, and calculate delta G. Once you have delta G, simply determine whether or not it's positive, negative, or zero at that temperature that you're looking at. You're looking at 260, 270, and 280. So evaluate those expressions and get your delta G. That is spontaneous enough. What do you expect delta G to be for 263? What's the sign of delta G for fusion going to be at 263? Negative, because it's spontaneous, right? So you're expecting that when you plug in, when you set T2 as 263, and you solve for delta S and delta H, and then plug them into that expression, you're going to get a negative number. What about 283? Does water spontaneously form ice at 283? No. So you solve for your delta H of 283, you solve for your delta S at 283, you plug them back into delta G is delta H minus T delta S, and you solve the expression, and you're going to find out that delta G is positive at 283. What do you expect delta G to be at 273.15? Zero. Because water reversibly changes phase between solid and liquid at 273. So delta G at 273 is going to be 0. This problem is very important because this problem tests the skills that I wanted you to develop by exam 1. Right? Exam 1, we asked you to get those changes in H with respect to temperature. And it builds on it a little bit because we introduced the entropy and the free energy into it. If you bombed exam 1, but there's a problem like this on the makeups, or even if there's a problem like this on exam 2, and you get this problem right, that's gonna tell me that you've already made up for what was lost on exam 1. So there's probably going to be a problem very similar to this. Practice this problem. Maybe I'll give you some practice problems that are similar to it, but make sure that you understand exactly how to do all of this. And if you can show me that you've got that problem ironed out, I'll have a hard time not giving you a pass in this class. Right? Of course, there's some other things you need to know, but what I'm saying is that'll really impress me. So, one more problem. We got a few minutes, and this is another one that's pretty cool conceptually, and it's important. We're going to look at the reversible adiabatic expansion of an ideal gas. Just randomly assign 1 mole of an ideal gas at 298.15 Kelvin and 10 atmospheres. We're going to expand it adiabatically and reversibly. Remember, reversibly, the internal pressure and the external pressure are identical. To a final volume that's twice the initial volume. And we want to calculate delta S. Now, this is one of those things where the actual process doesn't happen along a reversible path. So what you are left to do is to determine the initial state and the final state. And once you've pinpointed the conditions of the initial and final state, temperature, pressure, and volume, you are required to find a reversible path along which you can calculate delta S. Remember, delta S is dq reversible over t, so we have to find reversible paths between the initial state and the final state and integrate dq reversible over t along those paths to get delta S. So there's different ways to do this. For the sake of not confusing you too much, I'm going to suggest the appropriate paths. What you're going to find is that volume increases, it's an expansion. Temperature decreases because it's doing work, right? It's doing reversible work in this case. And so you're going to have some final volume that's larger than the initial volume, and you're going to have some final temperature that's lower than the initial temperature. So the appropriate paths to calculate delta S along are 2 appropriate paths. one path for the expansion could be an isothermal reversible expansion to bring you from initial volume to final volume. And then you can take a constant volume cooling path from the initial temperature to the final temperature. So you need to find the final volume, you need to find the final temperature, and then you integrate dq reversible over T along that isothermal reversible expansion path and the constant volume cooling. We already did these two paths last week. We showed them to you. For the isothermal reversible expansion, we end up getting the delta S for that path is NR times the integral of dV over T. We got that because we plugged in T being constant, two T terms canceled, and our, yeah. Anyway, so you remember that. And then the constant volume cooling path, we ended up integrating CV over T, right? So because the process is happening under constant volume conditions, we use the constant volume heat capacity instead of the constant pressure heat capacity. To do this fast, and I hope we can, what time do we end at 10:50 or 4:50? Okay, so I think we can do this in 20 minutes if we hurry through. But to do it, you're going to need your adiabatic relationships, and I'm just gonna, since the problem's already on the board, I'm just gonna put these guys up on the board for you real quick. So here are your expressions for the adiabatic reversible path, right? We did these derivations that related to final temperatures, pressures, etc. for the adiabatic reversible paths. Assume that CV in this case is equal to 3/2 R for a monatomic ideal gas.